Hello, eighth graders. So we are going to talk about absolute age dating of a rock. So this is getting a more precise age of what where a rock is on our geologic timeline rather than saying, oh, it's about so many years from today and all that kind of fun jazz. So this is like getting more of a like, this was 2.2 billion years ago sort of a thing. So still working with Middle School Earth Science Standard 1-4 and Middle School Life Science Standard 4-1, focusing in on the actual like 1-4, stating that we will construct a scientific explanation based on evidence from rock strata and how the geologic timescale is used to organize our 4.6 billion year old history, just because we're looking at the actual dates of it. But we're still looking at using more scientific backing to actually determine kind of how things are the way they are. But what I want you to get from this is what you're going to be able to do. So you should first be able to explain absolute age dating of rocks and other objects. You should be able to identify isotopes that allow for absolute age dating, and then be able to explain how scientists are able to determine the actual age of the Earth. These are all the most important things when it comes to actually like identifying like how old the Earth is. Weird. So if we move on, you should make sure you have for sure the whole group notes in front of you, if not all the notes. Okay, so absolute age dating is giving like the numerical age in years of a rock or an object. So instead of being like, my sister is older than I am and I'm older than my brother, because that's not telling you how old we all are. But if we were to state, my sister is 20, I am 18, and my brother is 16. That's giving you actual ages. That's essentially what we're coming down to in this whole progress. So what we need to kind of like rewind our brains all the way back to 6th grade science is the elements of our periodic table. All of the elements contain a very specific number of protons. We use that very specific number of protons to identify its elemental mass. So hydrogen has 1 proton, so we also identify it as element number 1. But the thing that makes all of these super fun and interesting is that the number of neutrons can then vary. So protons are positively charged, electrons are negatively charged, but neutrons are just there. And when an element has more than the designated typical amount of neutrons, that is when we start to develop isotopes. So isotopes are essentially just the same element with more protons. So you have hydrogen 1 with a mass number of 1. Then you have hydrogen 2, or deuterium, which technically can have a mass of 2 because you have a proton and a neutron within the nucleus, but you still only have that 1 electron and 1 proton. Then you can even take it one step further and have hydrogen 3, where you then have 1 proton and 2 neutrons in the same nucleus. When there are more protons than what the element originally calls for, that's where you get an unstable isotope. And that is important when we start talking about actual radiocarbon dating, because those are what help us determine how old something is. So stick with me. So isotopes are unstable, or the isotopes that are unstable, we also can call radioactive isotopes. So that would be like with our hydrogen 3. Hydrogen 3 is technically not stable. It doesn't like to sit in this way. It's like I have too many balls in the air and I just can't take it. So what happens is over time, a given amount of time, one of those extra neutrons actually turns into a proton. So now making hydrogen, which has a proton 1, so turning it into something with a proton 2, which is no longer hydrogen. It's actually helium. A proton 2 with 1 neutron gives you a stable helium-3 nucleus. Now, as we know, just because I want to explain this diagram for you quick, energy can neither be created nor destroyed. So once that energy moves like into changing that neutron into a proton, there's other energy that has to go out into like no man land. So that's when the neutron decays, energy then is released into the world, the universe. So the extra neutron decays and forms a proton. In this process, a new stable element forms. So no longer do we have unstable hydrogen 3, but now we have a very stable helium 3. 3 because there are 3 little things within our atom now. So we call that first unstable isotope a parent isotope. This is the original, this is the like life giver sort of a thing. And when it decays down into a more stable sort of position, we then call that a daughter isotope. Now, why parent and daughter, I'm not 100% sure. I do just know that typically when we talk science, a lot of things are referred to in the more feminine sense. So that's why it's parent to daughter instead of like parent to child or parent to son. I don't know. But the daughter isotope is then a stable, so it's not juggling too many things. It can handle what's going on, but it's the more stable version of what the parent was. Now, you can read into that the way you want to. I'm just going to leave that there. Okay? But what we need to understand is that the first isotope, the unstable one, is the parent isotope, and then given time, it can then transition into the more stable daughter version of that isotope. And then in turn, it also turns it into a stable element. Okay? Yes, sometimes you can take a neutron and add a proton, and sometimes it still stays the same element, but 9 times out of 10, you are going to move from one element to a different one. Typically, the next step or steps down the element of the periodic table. Now, when we look at every parent isotope, we have noticed that they decay at a very steady rate. Now, this typically is measured in time, and we actually call those amounts of time half-lives. It's the time it takes for half of the parent isotope to actually decay into the new daughter isotope. So one half-life means that 50% of that original parent is now transferred down into the daughter isotope. So half-lives all depend on the element. Some half-lives are just milliseconds, to where by the time I even explain millisecond, some have already decayed multiple times. Other parent isotopes actually take billions of years. So those are the ones that we're looking at. Yes, the ones that decay over very quick amount of time are awesome. That's usually how we then start to identify brand new elements, or how we get larger in our periodic table, sort of a thing. But the ones that take a really long time are the ones that help us then determine the age that something was in relation to where we are today. So this little graph is a little bit better description of what a half-life is. So you have the full parent isotope in all red. No matter how much time actually passes, but the first half-life means 50% of that red is now gray, and then you still have 50% of the red remaining. Then the next half-life, you have another 50%, or you're left with 25% of the parent isotope, and 75% of the daughter isotope now exists. And it keeps going on, okay, to where eventually you hit an exponential rate where it doesn't 100% ever really turn into the full complete daughter isotope. That's just what's up, okay? So that is the end of my whole group lecture, just to kind of like make sure that you know what's going on with the meat and potatoes of all this. So if you are now going to go watch the video or do the textbook notes, awesome. I'll see you later. If you're sticking around for the PowerPoint, just give it one more second and I'll continue on. So typically when we talk about radiocarbon dating, we're talking about the element of carbon. More specifically, we are talking about carbon-14 or C14. Now, why do we look at C14? Well, that's because carbon-13 is the most abundant version of carbon in our world. There is a lot of carbon-14 out there, which we do take in as living things. We are constantly taking and giving carbon. Now, what does this mean? Well, now I'm going to make you think back to last year. So the photosynthetic and the, oh my goodness gracious, now I'm not going to remember it, cellular respiration cycles. Okay, so we as animals take in oxygen and we release carbon into the world. Then we have plants that take in carbon and release oxygen into the world. And then it's just this constant cycle. So we then take in carbon through our foods, because if all of our plants are taking in carbon or our other animals are releasing carbon, upon their death or their consumption, there's still carbon in them. So we are constantly taking in carbon. A small percentage of that carbon is carbon-14, which takes 5,730 years for half of that to decay into nitrogen. So we radiocarbon date carbon because we actually have this science and these numbers to be able to actually explain why things are the way they are. So what does this mean? Well, that means that since we know the typical amount of carbon that an organism should have in them in relation to the amount of carbon-13 that we constantly are taking in and giving out, we are able to accurately date any item or fossil or rock all the way back to 60,000 years from today. So that means we look at the amount of carbon-14, or the parent isotope, in any given thing. You do a lot of math, which is not a forte. All of my kiddos know this. But then we look at how much of the daughter isotope, or the nitrogen-13 remains, nitrogen-14 remains, and then we're actually able to accurately date. So we know that if there is like half is carbon-14, half is nitrogen-14, we know that that particular item is 5,730 years old from today. So that's why it's such a big deal. Like I said, carbon-13 and carbon-14 are constantly in our atmosphere. They're constantly being ingested through all of our different foods and things like that. And then it decays down into nitrogen-14 at a very constant rate of about 5,730 years. So again, this is where it gets a little iffy and like my brain gets a little fuzzy when it comes to numbers. So if you were to have 10 grams of carbon-14, okay, 10 grams, and you look at that, and if you now see that there is 5 grams, you know that 5,730 years has passed since that organism died. Because here's a weird thing, as soon as you die, you stop taking in carbon. Weird, to where it's a lot easier for nitrogen to build up in your system. So that then if you look at something that you know originally had 10 grams of the carbon-14 and it's down to 1.25 grams, that means 3 half-lives have passed, which means if you take that, I need my calculator, because again, I don't do numbers. So if we have 5,730 we have then seen 3 half-lives pass, so we multiply that by 3, that means that that specific rock or object or whatever is 17,190 years old. Now, don't ask me to do the math in between all that, I don't know. But scientists do, and that's what really counts in the end. So that's why we use carbon-14. Now, when we start talking about rocks, this is really easy to do in like preserved remains and things like that, because like you can just, it's the way it is. But when we look at rocks, we have to take a couple more things into consideration. So bear with me. Igneous rocks. Okay, igneous rocks contain a lot of uranium-235 because it gets trapped within the minerals that just happen naturally, quartz, in igneous rocks. As soon as the isotope is trapped, they begin to decay into lead-207. So objects we use carbon-14, but when we start looking at rocks, we're looking for the amount of uranium-235 as compared to lead-207. Okay, igneous rocks, super duper easy. We know that the moment it solidifies, that was the date of birth or death, however you want to look at it. And then we can then start looking at the amount of lead to determine how long this rock has truly been around. Now, sedimentary rocks. Okay, remember, igneous rocks come from volcanic eruptions or really slowing down volcanic cooling, things like that. Sedimentary rocks are little bits and pieces of rocks that have been broken down through weathering and erosion and all that kind of fun jazz. So because sedimentary rocks come from a variety of weathered rocks from different locations and then are deposited into different areas, which then goes through compaction and cementation and all that fun jazz, the age of the grain, you get the age of the actual grain rather than the day that it was deposited. So the age of the grain is always going to be older than when the sedimentary rock actually formed, because those grains and those sediments came from other rocks that had a lot of time to go through this process, sort of a thing. So it's not as easy to date sedimentary rocks as it is to date igneous rocks. Now, why don't I have a little blippet for metamorphic rocks? Because you thought that sedimentary rocks were really, really hard. Metamorphic rocks are just a whole new game, because now you have to take into consideration the heat and pressure we put it under to transform one of these two rocks, which already are going to be a lot older, into a new metamorphic rock. It's not easy. So typically, paleontologists, things like that, they're looking for igneous rocks to help us radiocarbon date anything, just because they're the least transformed over time. So if that makes sense, I really hope so. But yeah, so these aren't the only isotopes we ever look at. Obviously, we talk about radiocarbon dating objects and fossils and things like that, and we talk about uranium 235 when we're talking about like radiocarbon dating rocks and igneous rocks more specifically and things like that. But we look at other things too, because different isotopes have half-lives that decay over different rates of time. So you must have enough parent isotopes to daughter isotope ratios. So this is just kind of a compilated list of like what different geologists are looking at in order to radiocarbon date something. And typically, we don't just rely on one point of data. We rely on multiple because it gives us a more accurate reading. So we look at things like potassium-40 because it takes 1.25 billion years for it to decay into argon-40. But then we go all the way down from uranium-238, which is just 2 more extra neutrons, then uranium-235, or sorry, 3, see if I can count today, holy Hannah, all the way down to rubidium-87 because it takes 48.8 billion years to decay down into strontium-87. That means if we're looking at the age of the Earth, one parent isotope of rubidium-87 isn't even middle aged down into strontium-87. So by looking at half-lives that are much, much longer than, say, the 5,730 of carbon-14, if we look at parent isotopes that have a longer half-life, it gives us a more accurate older age dating option. So what this means is we can date something back further than just 60,000 years. We can date it back all the way to the actual birth of our universe and our Earth. And this sort of a thing is what we use to actually age the Earth. So, cool, fun tidbits. I love this sort of information. So the oldest rock formation ever found was actually found in Canada. And with the radiocarbon dating that they were able to do using multiple isotopes, geologists have determined that that actual formation falls between 4.03 billion years to 4.28 billion years old. Now, they've also found mineral zircon in igneous rock. So obviously we like to look at igneous rock because it's the least disturbed, which gives us about an age range of 4.4 billion years old. So just by looking at those two data points, we're looking at the age of the Earth being somewhere between 4.03 and 4.4 billion years. Already just falling along the lines of uniformitarianism, that we have a very, very old Earth. Awesome. Now, because we weren't the only thing created in the Big Bang, weird, I know, we also started taking rock samples from the moon and meteorites, and I believe, I don't have this written down, but I am like almost 100% like thinking that we've taken rock samples as well from Mars to be able to do this same sort of age dating process, just to ensure that our numbers are kind of going the way that we think they are. But by looking at those two data points, we're looking at an actual solidification age of about 4.54 billion years old for our entire universe. Because while we were just this hot ball of magma for a while until we started cooling down and solidifying into an actual like object, plus we have to remember how the moon was formed. So we had Theia, that big old asteroid that came and hit the Earth, which then kind of shot out all this dust and dirt and rocks, which then actually formed into the moon. So that would be the actual, like, it would be slightly younger than our Earth, just because obviously our Earth had to be solidified before it, like an impact from an asteroid actually mattered, sort of a thing, to where we are really, really confident in being able to say that our Earth and our universe is actually 4.6 billion years old. Now we take that 4.54 and round it up to 4.6. It just rolls off the tongue a little bit easier. But by looking at all of that, that's how we can support the principle and the theory of uniformitarianism, that the universe and the Earth is actually really, really old. Now, we would not be able to do any of this without the technology that we have been able to actually develop and analyze these sorts of things. So, kind of weird and crazy. Yeah. I know this was a lot of like big world thinking that, like, if you're anything like me, it still doesn't 100% make sense, and that is completely okay. It doesn't 100% make sense to me either, but I understand how someone who enjoys math a little bit more than I do could actually like understand this. So if you have any questions, comments, concerns, reach out. I will try my best, and if not, I will refer to someone who does. Oh, oh my goodness, it was so obnoxious being that I'm about to sign off. So anyway, if you have any questions, please reach out. Make sure you complete your exit slip that goes along with this, and I will see you later. Thanks, guys.